Welcome back, everyone. Today's explainer is, well, it's basically a detective journey straight into the mechanical heart of our control systems. I mean, if you've ever stood there staring at a silent pipe or a dead HVAC unit, just scratching your head wondering what went wrong, you are absolutely in the right place. Today, we're going to learn how to stop the endless parts guessing and start some serious, systematic troubleshooting for solenoid valves. So get ready to build up that deductive logic.
Okay, let's dive into this. Here's our logical roadmap for today. First, we'll meet the solenoid valve. Second, solenoids in the wild. Third, symptoms and common failures. Fourth, the diagnostic investigation. And finally, we'll wrap up with the troubleshooting golden rule.
Section 1. Meet the solenoid valve, profiling the primary suspect.
So, before we can effectively interrogate how a component actually fails, we really need to understand our primary suspect, right? At its core, a solenoid valve is simply a device that converts electrical energy into mechanical movement to control fluid or gas flow. Think of it as the vital bridge between a system's electrical nervous system, the controls and wiring, and its mechanical muscular system, which is the physical piping and fluid dynamics. It literally translates an electrical thought into a physical action.
Let's move on and see how this actually builds. Looking inside, we've got several main components working together in perfect harmony. There's the solenoid coil that creates the magnetic field, the plunger or armature that physically moves, a spring to return that plunger to its resting state, the valve body itself, the ports where fluid enters and exits, and of course the internal seals. It's also worth noting there are two main variants here. You've got direct-acting valves where the magnetic field lifts the plunger directly, and pilot-operated variants which cleverly use the system's own line pressure to help open and close that main seal.
Now, these valves usually come in two primary resting states, which is absolutely crucial to know when you're troubleshooting. A normally open valve, or NO, allows flow freely until it's electrically energized to shut. It's open by default. Conversely, a normally closed valve, or NC, blocks the flow entirely. It just sits closed until the coil receives power, which creates the magnetic field that lifts the plunger to open the path. Knowing a valve's resting state, that is step one in figuring out if it's acting normally or misbehaving.
Section 2. Solenoids in the wild, where the suspects operate.
All right, let's transition out of the theoretical and into the field. You're going to find these suspects operating literally everywhere. From controlling refrigerants in massive HVAC units to directing flow in municipal water and pneumatic systems. They're critical in gas control networks, and honestly, they're the unsung heroes of heavy industrial equipment and automation. And the really crucial takeaway here is this. Whether that valve is being commanded by a highly advanced PLC, a simple electrical relay, or just a basic wall thermostat, the underlying physical operation of that coil and plunger remains exactly the same.
Section 3. Symptoms and common failures, building the rap sheet.
When a system goes down, we need to treat it like a crime scene, where your physical clues map directly to the culprits. And this brilliantly illustrates how mapping those clues works. If the valve is loudly humming or buzzing, the culprit might be mechanical wear binding the plunger, or maybe an AC voltage issue. But what if it's energized and there's no flow? Well, you might be looking at a valve stuck closed, a severe blockage, or simply missing voltage. If it's de-energized but still flowing, your valve is likely stuck open, has damaged seals, or maybe some dirt is holding the plunger up. And if you notice the coil is physically overheating, you're usually dealing with a shorted coil or incorrect voltage. Basically, every single clue narrows down your suspect list.
Beyond those initial symptoms, we've got to keep our eyes peeled for other common failures. You might encounter a totally burned or open coil that does absolutely nothing when powered. You could find a weak or damaged internal spring that just fails to reset the valve. Damaged diaphragms or seals are super common wear items too. Sometimes it's just an incorrect differential pressure preventing a pilot-operated valve from shifting at all. But I really want to emphasize that last point, contamination. Simple dirt and debris are incredibly frequent offenders when it comes to valves sticking. Seriously, a tiny piece of pipe scale can bring an entire industrial process to a grinding halt.
Section 4. The diagnostic investigation, step-by-step deductive logic.
Okay, now we shift into active detective mode. Here is our definitive step-by-step investigative sequence. 1. What should the valve be doing right now? 2. Is the controller actually commanding it? 3. Is the correct voltage present? 4. Is the coil electrically healthy? 5. Is the mechanism physically operating? And 6. Is the pressure and flow adequate? We use this exact deductive stepping for a very specific reason. It prevents us from chasing ghosts. If you start unbolting the valve body before verifying the controller is even sending a signal, you are going to waste hours of your day. No one wants that.
So let's pose a practical mystery to test this out. Picture this. The controller is actively calling for the solenoid valve to open, but you look at the system and there is absolutely no fluid flow in the pipe. Where do you even start your investigation?
Well, what's really interesting here is that our first physical action isn't on the valve mechanism itself at all. We start at the macro command level. You must verify the required voltage by reading the coil's nameplate, and then safely use your multimeter to measure across the coil to ensure that exact voltage is actually arriving. Because think about it. If the controller says open, but the multimeter reads 0 volts at the coil, the valve isn't your problem. Your problem is somewhere in the wiring or the controller.
Now, if the correct voltage is arriving, we transition down to the micro level, coil health. And it is absolutely critical here that you turn the power off. With the power safely removed, you check the coil's electrical resistance with your meter to identify if the internal windings have failed open or shorted out. Once you know the resistance is good, you can power it back on and use a magnetic tool to verify a magnetic field is actually being produced by that energized coil.
Testing for that magnetic field is really the great divide in our investigation. It acts as a strict dividing line between an electrical or control failure and a physical, mechanical failure. If you have proper voltage, good resistance, and a strong magnetic field, boom, your electrical side is completely cleared. You've literally just eliminated half of the suspects on your list in a matter of minutes.
Because the electrical side cleared, we now know for a fact we're dealing with a mechanical or flow issue. Now, and only now, do we physically open the valve body. We're hunting for internal dirt, blockages holding the plunger firmly in place, damaged rubber seals, or worn metal parts that are binding the mechanism and preventing that magnetic field from doing its job.
We finish our investigation by looking at the system's vital signs. You need to verify the inlet and outlet differential pressure and confirm the valve is actually installed in the correct flow direction. This is so important because a mathematically perfect, brand new solenoid valve still won't work if the system pressure is inadequate to assist the pilot, or, if a previous technician simply installed the valve backward against the flow arrows. It happens more often than you'd think.
Section 5. The Troubleshooting Golden Rule. The Ultimate Technician's Directive.
So this brings us to the core philosophical takeaway you need to carry with you on every single job. The crucial point is right here. Do not replace the solenoid valve simply because it is not operating. First, determine whether the problem is electrical, control-related, mechanical, or related to system pressure and flow. Basically, stop the guesswork. Do not just be a parts changer. Always verify the why before you grab your wrench and start swapping components.
Let's summarize and cement this definitive 5-part investigation sequence in your memory one last time. Step 1, verify the command. Step 2, confirm the voltage. Step 3, check the coil health. Step 4, inspect mechanical operation. And Step 5, validate system pressure and flow. If you follow this path, you are going to isolate the real culprit efficiently, safely, and accurately every single time.
Which brings us to our final takeaway and a question I really want to leave you with. The next time a control system halts and everyone is standing around staring at a silent pipe waiting for answers, will you just blindly swap the part and hope for the best, or will you use your new deductive logic to actually solve the mystery? Thank you so much for joining me for this explainer. Keep learning and stay focused out there.